Hi everyone, I'm Milad and I'm an AI researcher working in Singapore. This video is a technical talk about training generative models when you don't have that much data, including scenarios like limited data, few shots, and zero shot. This talk is based on our recent survey on the topic, where we have reviewed more than 200 published research papers, analyzed them, and proposed categories for generative tasks and approaches. This is the outline of the talk. It's going to be a bit lengthy. First, we will discuss the high-level picture of what we call generative modeling under data constraints, or GMDC. Then we will discuss a brief background about generative models. What does generative modeling mean, and what are the popular image generation models? Then we will discuss uh, different categories of generative tasks, the major challenges of training generative models under data constraints, the comprehensive review of the proposed approaches, and finally, the research landscape analysis. First, we start with the discussion of the high-level picture. In recent years, we have seen a tremendous progress in image generation models. Generative adversarial networks, or GANs, which are presented by Jan Goodfellow in NeurIPS 2015, are among the first models that are using deep neural networks for image generation. As you can see, at that time, the quality of the generated images was not that good, but this paper shows the possibility of image generation with deep neural networks. 6 years later, we have StyleGAN2 in CVPR 2020. And as you can see, the quality, diversity, and details of the generated images have improved a lot. And now it's really hard to distinguish them from real images. 2 years later, in CVPR 2022, we have latent diffusion model. Latent diffusion model is capable of generating images with a large amount of details. For example, this landscape image. And it has also conditioning mechanism, meaning that you can give this text prompt as input, something like an epic painting of Gandalf the Black, summoning thunder and lightning in the mountains. And the generative model follows the text prompt and gives you the output image. And as of now, in 2025, the image generation models are progressed a lot. The quality, diversity, and instruction following capability of these models have improved a lot. For example, these are some samples from Grok Imagine. And there are other multiple good models like the recent versions of Stable Diffusion, GPT, Gemini, Leonard AI, Midjourney, and others. But there is something in common between all these generative models. If you want to train these models from scratch, it will need a lot of data. For example, StyleGAN 2 is trained on 70,000 human face images from FFHQ dataset, or latent diffusion is trained on 400 million image text pairs. If you don't have that much data, you won't be able to train these models and get the same quality. And this is what this talk is exactly about, training generative models when you have data constraints. Based on what we have in the research literature, we propose different scenarios. Limited data is when you have 50 to 5,000 training samples. Few shot scenario is when you have 1 to 50 training samples, and zero shot is when you have no training samples. Next, we discuss the background of generative models. And here we discuss three main things. First, we discuss the definition of domain and generative modeling. Then we discuss the difference between conditional and unconditional image generation. And finally, we will briefly discuss popular image generation models. Note that here we don't consider data constraints, and these are some common concepts shared among all image generators. We start with discussing the definition of domain and generative modeling. A domain consists of two components. First, we have a sample space. This is inspired by statistics. A sample space is the set of all possible outcomes of an event. And alongside that, we have the data distribution. So these samples follow this data distribution denoted by p data. As an example, we can consider Flickr Face HQ dataset or FFHQ dataset as the domain of image of human faces. As you can see, all images in this domain are human faces, but they are different in race, skin tone, age, pose, and other attributes. But the common thing between all these images is that they follow a single data distribution. After defining domain, we define generative modeling. Given a set of training samples from a domain, meaning that we have a set of training samples that follow this distribution. Generative modeling aims to learn to capture this distribution of the data. And the result is a generative model. We usually show it by G, which encodes a probability distribution. And we show this probability distribution by P model. The learning objective is to make this P model statistically similar to P data. After training, G can generate samples following P model. For example, we have some samples of human faces dataset, P data here. We train a generative model on these samples, and it kind of approximates this P data. After that, we can sample some latent code and generate new samples that didn't exist before. Next, we discuss the difference between generative and discriminative modeling. Discriminative models, you are probably familiar with these models. Classifiers are usually discriminative models. And the idea in the discriminative models is to just learn the boundary, and we don't have interest in learning the distribution. For example, if we have two classes of cats and dogs, the discriminative model is just interested in learning this boundary. After learning this boundary, for an unseen sample, it's either mapped over here, which is classified as cat, or mapped over here, which is classified as dog. But generative models are interested in learning the distribution itself. So they are not kind of learning the boundary, they are learning the whole distribution of cats and the whole distribution of dogs. Later, after learning this distribution, the knowledge can be used for sample generation. For example, if you consider these dots as training samples in this distribution, we can sample somewhere in between these training samples and generate a new sample that didn't exist before. Another important concept that we will discuss in background of generative modeling is the conditional and unconditional image generation. Usually, after training a generative model, image generation is performed in two steps. First, we sample a random noise or a latent code from this distribution, and then we use this latent code as input to the generative model or G, and generative model transforms this latent code to a new sample or new image. This is called unconditional image generation because we don't have conditioning mechanism to restrict image generation. If we add an additional condition denoted by C to steer sample generation towards this C, we call this a conditional image generation. Now G is a function of both Z and C. As an example, this condition could be a class label. For example, here, in addition to latent code, we have this class condition. If we pass class condition of peacock and sample a latent code, the model will generate an image of a peacock. For the same C, if we sample different latent codes, we will see various images of peacock in the output at the ideal case. This conditioning could be on text prompt. Here, C is a text prompt. We condition the generative model on this text prompt, sample a latent code, and the model generates an output image based on this text prompt and the sample latent code. We can also have conditioning on layout. For example, here we have C as a layout. This is a layout of the image that is going to be generated, including some bounding boxes. For example, this is a bounding box for traffic lights. This is a bounding box for cars and other objects. And as you can see in the generated images, we have some diversity and variation on other objects, but we have traffic light on all these generated images. And finally, we discuss popular image generation models, including variational autoencoder, generative adversarial networks, and diffusion models. To discuss variational autoencoder, first we need to understand the concept of autoencoder. The idea of autoencoder is first proposed in this old Nature paper. Here, authors describe how a neural network trained with backpropagation can learn internal representation. And among this discussion, they include using a bottleneck hidden layer, which compresses and reconstructs the input, which is basically what we call autoencoder. The most popular paper, which introduces autoencoder, is this ICML 2008 paper from Yashua Benjiu's group. This one is also a very influential paper in representation learning. And based on this paper, an autoencoder consists of two networks. We have an encoder, which learns to map input image to a low dimensional latent representation. The input image is X and the latent representation is shown as Z here. Then we have decoder, which aims to reconstruct the image using this latent representation. So the input is X and the output is the reconstructed X, denoted by X hat. And based on this, the learning objective is the difference between input and reconstructed image. Autoencoders usually focus on dimensionality reduction, meaning that usually after training autoencoder, we discard D and keep E as a dimensionality reduction network and use its output for different tasks like classification. But one drawback of autoencoder is that its latent space is irregular, and because of that, we can't use it for sample generation. For more details, the irregularity of autoencoder's latent space is the direct result of learning a deterministic mapping instead of learning a probabilistic one. The latent space of a regular autoencoder is discontinuous and irregular, meaning that there are some holes and gaps within this learned distribution. And if you sample from these holes and gaps, and we don't know where it is, if you sample a random latent code and it's it's within these holes and gaps, we will end up in generating meaningless, blurry, or chaotic outputs. Variational autoencoder is introduced by Kingma in this ICLR 2015 paper, and it aims to address this irregularity. And it does it by aiming to learn a smooth, continuous, and structured latent space with two changes. First change is by learning a probabilistic encoder and decoder. Now, instead of outputting Z or latent code, the encoder outputs the mean and standard deviation. And this latent code is sampled based on this mean and standard deviation. This adds a probabilistic kind of aspect to the encoder and decoder. Another thing is that they add a regularizer to push all the learned distributions towards the center of the latent space. And in this way, they try to kind of prevent learning these holes and gaps. And this regularizer is implemented using the KL divergence between the learned distribution and a normal distribution with mean of 0 and identity matrix as standard deviation. And finally, a very popular version of variational autoencoder, which is used in most of recent powerful image generation models, is vector quantized variational autoencoder, introduced in this NeurIPS 2017 paper by DeepMind group. And what they do is to add a tokenizer, which is a visual tokenizer, which quantizes the embeddings into visual tokens. And this is used to kind of mitigate the challenges of direct maximization of the likelihood. This becomes very challenging in image space, which is very high dimensional. But in this tokenized embedding space, it becomes a bit more easier. And that's why it enables learning large scale models. Next, we discuss GANs, which, as mentioned before, are introduced in this NeurIPS 2014 paper by Jan Goodfellow. A GAN consists of two networks. We have a generator that learns to generate images using input noise or latent code. So we pass this input noise or latent code to the GAN, and it transforms it to an image. And then we have a discriminator, which learns to distinguish between fake and real images. Real images are coming from our dataset. Fake image is generated by generator. So the goal of the generator is to fool the discriminator that this generated image is real. And on the other hand, discriminator wants to be able to kind of distinguish real and fake images. These two networks compete with each other in this game, and they learn and grow together. Usually, we call this competition as a min-max game because of this value function we use for training GANs. As you can see, this value function is based on the score of discriminator for real and fake images. So d of x is the score of discriminator for real images. D of g of z is the score of discriminator for fake images. Discriminator wants to increase score for real images and decrease score for fake images. So it wants to maximize d of x and it wants to minimize d of g of z. And because of that, it wants to maximize this value function. On the other hand, generator wants to increase the score for d of g of z. It doesn't have any influence on the score for d of x. And based on this value function that we have, it can do it by minimizing this value function. And that's why we call it a min-max game. Finally, once d and g are trained, we usually discard d and use g for image generation. After this classic GAN, there have been numerous studies to improve this classic GAN. And in the upcoming slides, we will discuss some major advances in GAN literature. We start with this conditional GAN or CGAN. As you see, this is the paper for CGAN. And the first author is Mehdi Mirza. He is one of the co-authors of original GAN paper. And what they do, they add a class label C along with the latent code Z as input to the GAN. So now GAN has two inputs, the latent code Z, which is a kind of random noise, and C as class label. Because we have this label as input to G, we also have labels for our training samples in real images. And because of that, this training requires a labeled dataset, and it's a supervised learning. Note that in original GAN, we don't have any labels, and it's an unsupervised learning. This figure shows some generated images using this CGAN on MNIST dataset, which is a dataset of handwritten digits. Each row shows a different label. For example, first row, you can see generated zeros. Second row, you can see generated ones, and you can see other numbers too. Another important paper is Deep Convolutional GAN or DCGAN, which is presented in iClear 2016. First author is Alec Radford, and you may know his other important works like GPT-2 or CLIP paper. In DCGAN, what they do, they replace fully connected layers of original GAN with convolutional layers. Convolutional layers can better capture the neighborhood information, the local information, and because of that, they can improve the image generation. In addition, their second major contribution is to use batch normalization in both G and D. I think at that time, the batch normalization was just recently introduced. And this paper is probably the first one that applies batch normalization for GANs. And as you can see, using these two contributions, they were able to improve image generation quite a lot. Now we have a bit more details compared to original GAN paper, and we have colorful images. But still, you can see lots of artifacts in generated images. Next work is auxiliary classifier GAN or AC GAN, which is presented in ICML 2017 from Google Brain. It was Google Brain at that time, but I think it was merged into DeepMind in 2023. And now we know it as Google DeepMind. Anyway, ACGAN has one major contribution. In addition to real and fake classification we have in original GAN, they ask discriminator to estimate the class label of the images. For real images, we have this class label because it's a labeled dataset. And for fake images, we also have the class label because we pass it as input to the generator. So here, D has another task and it provides it another supervisory signal. And because of that, D becomes more powerful. And this leads to training a more powerful conditional generator. As you can see, compared to CGAN, ACGAN is more powerful. CGAN was just able to generate images from MNIST dataset, which is simpler dataset compared to ImageNet used here. The name of next paper is a bit hard to pronounce, so we use this tweet from Jan LeCun. And based on this, we should call it Wasserstein-GAN, or we can simply call it WGAN. WGAN is proposed in ICML 2017 from Facebook AI Research. The acronym was FAIR and it was cool. People used to use this affiliation as FAIR, but now it's gone. We know it as Meta AI. And what they do, instead of real and fake classification in the discriminator, they want D to use Wasserstein distance to measure difference between real and fake images. Because D is not performing real and fake classification, sometimes they call it a critic. And as you can see on this figure on the right-hand side, WGAN has better gradients compared to original GAN. And this results in improving convergence, preventing mode collapse, and helping with a better training stability. Next paper is progressive growing of GANs or ProGAN, which is presented in iClear 2018 from NVIDIA. First author is Tero Karas. He has lots of good papers. I usually enjoy reading his papers. So what they do, they have a simple idea. They start with learning smaller networks. So as you can see on this figure, at the beginning, the network has less layers. And as training goes, they increase the number of layers. And what happens here is that at the beginning, Progan learns simple concepts, and then it learns more and more complex nuances in the data distribution. And in this way, they were able to generate very decent images. So the quality of the images has improved a lot, but still you can see some artifacts here and there. Next important paper is Big GAN, which is presented in iClear 2019 from DeepMind. And they use self-attention to cover patches in different locations of image. The idea is inspired from SAGAN paper. And in addition to that, their major contribution is that they enable high resolution image generation with two main contribution. First, they use truncation trick on latent space. Another one is very simple. They just use a larger batch size. And as you can see, they were able to generate decent images similar to ImageNet dataset. Next work is style-based generator or StyleGAN, which is presented in CVPR 2019 from NVIDIA. This is the same group proposed ProGAN paper. And what they do, they improve processing latent code for better image generation. And they do this by mapping Z to an intermediate space called W using a mapping network. This enables to disentangle and learn different styles during image generation. And these are some of the generated images from StyleGAN. The quality and amount of detail in generated images uh, are awesome. So for the first time I saw these images, I was really shocked that GAN can kind of generate images with this quality. Because prior to that, usually you can see lots of artifacts in generated images. But for the first time in StyleGAN, it was like some of generated images uh, don't have any artifact, and it's really hard to distinguish them from real images. And this is another cool feature of StyleGAN. They are able to do style mixing. So for example, here, the course style is coming from source B, and they kind of mix it with the style of source A, and they are able to generate new fake samples. After that, we have StyleGAN 2, which is CVPR 2020 paper from the same group. And they redesigned the architecture of StyleGAN by using modulation and normalization. And they have StyleGAN 3 also, the same group, NeurIPS 2021, and they address aliasing in this paper. Based on what we see in the literature, StyleGAN 2 is the most popular GAN for generative modeling under data constraints. The final generative model we are going to discuss is diffusion model. Diffusion models are introduced in this ICML 2015 paper from Stanford University and Berkeley. And this paper introduces the core concept of diffusion probabilistic models inspired by non-equilibrium thermodynamics. Diffusion models consist of two main steps. First, we have forward diffusion process, which consists of multiple steps. The input image, the real image is used as input, denoted by x0. And in each step, a low-level noise is added to the input. And the scale of noise varies at each step. The training data is progressively destroyed, and finally, we will have a pure Gaussian noise. The reverse diffusion process, also known as denoising process, has same iterative procedure but backwards. As you can see, it starts with xt, pure Gaussian noise, and in each step, the noise is sequentially removed, and at the end, we have the reconstruction of the original image. In the forward diffusion process, we denote the uh, training sample as x0, which has this p of x0 distribution. The noisy versions of this sample are denoted by x1, x2, and xt. So these are the noisy versions after each diffusion step. And these noisy versions follow a Markovian process. So the distribution of xt given xt minus 1 is a Gaussian process. The important property of this formulation is the possibility to directly sample noise at each diffusion step t. So the distribution of xt given x0, which is input training sample, can be formulated as you can see. And they usually use a reparameterization trick for this sampling. So xt can be written as a function of x0 and the noise itself at time step t. For reverse diffusion process, which also we call a denoising process, we can create new samples starting from the random noise itself and following these reverse steps. So the distribution of xt minus 1 given xt is also a Gaussian process. And in diffusion models, we want to train a neural network to approximate these steps. And we usually use a UNet for this training. And what this network is trying to do is to predict the mean and variance of the noise at time step t based on the input. And it is trained to maximize the posterior distribution of the real samples as formulated here. One important follow-up work is this NeurIPS 2019 paper from Stanford University, which basically introduces score-based diffusion models. This approach is called noise conditional score network, or NCSN. And instead of learning to denoise, the NCSN framework learns to estimate the score function. This score is defined as the gradient of the PDF with respect to the data itself. This NCSN paper, for the first time, shows that diffusion models are capable of generating images which has comparable performance to GANs. And another very important follow-up is denoising diffusion probabilistic models, or DDPMs, proposed in this NeurIPS 2020 paper from Peter Abel's group in UC Berkeley. Peter Abel has also lots of other interesting papers, one of them which is model agnostic meta-learning. Here, they propose a new simplified framework which fixes the variance and rewrites the mean as a function of noise during this diffusion and reverse diffusion procedure. And based on that, the network is trained to predict noise itself instead of mean and variance. This results in a simple loss. They call it a loss simple. And the popularity of diffusion models for image generation starts from here. After this new simple loss, now it's easier to understand the procedure of denoising and easier to train diffusion models. This paper is also the first paper to show the capability of diffusion models to generate images which are better than GANs. So these are compared to the GANs in 2020. Finally, we have this latent diffusion model, or stable diffusion model, which is a CVPR 2022 paper. Latent diffusion model has two major contributions. First one is to train the denoising network, or reverse diffusion in the latent space instead of image space. So what they do, they use an autoencoder to map input image to the latent space. In addition to that, they have a cross-attention mechanism for conditioning. So the image generation can be conditioned on multiple things, as an example, on a text, on an image, on representations, semantic maps, and others. And for each of these, they have their own related encoder to map these conditions to the latent space. And finally, the denoising is being done in the latent space. Here, they use a standard unit similar to other works. They use simple loss, and they use cross-attention mechanism to condition image generation to whatever input we have in the right-hand side. After discussing the high-level picture and background of generative models, we start to discuss the technical details of generative modeling under data constraints. And the first part is uh, the classification of image generation tasks. Here we propose a taxonomy of generative models in GMDC. This is our proposed taxonomy. So we basically reviewed more than 200 papers and classified the generative task on these papers based on 5 attributes. We have conditional or unconditional image generation as first attribute. We have the usage of pre-trained generator network as another one. Either images are used as input or not is the third one. Whether the text prompt is available is the fourth attribute. And finally, is there any cross-domain adaptation or not is the fifth one. Also, for each of these tasks, we have mentioned which data constraints they are compatible with. Limited data, few shots, and zero shot. So we start with task 1. First task is unconditional generative modeling under data constraints. We call it UGM1. And here we are given K samples from a domain, and the objective is to learn to generate diverse and high quality samples from that domain. In this setup, we need to learn a generator from scratch, usually using only 50 to 5,000 samples. And there is no other side information available for this. As an exemplar solution for this, ADA paper proposes an adaptive data augmentation approach to learn again from scratch. And some examples are training a GAN from scratch on breast cancer dataset using only 2000 training samples. As you can see, the generated images have very good quality. Or training a GAN using 1.3K images of face paintings collected from Metropolitan Museum of Art. And as you can see, the generated images have very good quality. The main challenge on this task is overfitting to training data or non-converging loss. As an example, here we have an analysis from ADA paper. They show that when we have 20,000 samples, the discriminator is being overconfident, which is an indication of overfitting. For example, in this plot, the blue line shows the score of discriminator for real images, and orange line shows the score of the discriminator for fake images. As you can see, when training goes on, the discriminator becomes more and more confident about real images and kind of overfits to them. Second task is unconditional generative modeling under data constraint with pre-trained generator and cross-domain adaptation. We call this UGM2. And in this task, we are given a pre-trained generator on a source domain. For example, here we have a pre-trained generator on FFHQ dataset. And this generator is trained with numerous and diverse samples. And because of that, it is capable of generating high quality and diverse images from source domain. In addition to that, we have K samples from a target domain. Here, target domain is sketches. And our objective is to learn to generate diverse and high quality samples from target domain. So we want to learn a generator called G of T here to kind of perform this image generation for us. And this task aims to transfer the knowledge from source domain to target domain with limited data. As a solution, for example, we have this CDC paper, which introduces a regularizer based on cross-domain correspondence. And this regularizer helps to adapt a pre-trained GAN on FFHQ to sketches using only 10 samples from target domain. So this is a few-shot image generation paper. On the bottom, you can see images generated from source GAN. And as you can see, the images have good quality and diversity. And CDC wants to kind of keep this knowledge, the knowledge about facial structure, pose, and all these things, and just change the style to the style of sketch. The major challenge in this task is that once we are fine-tuning the source GAN for target domain, there is a high chance of degrading the source knowledge. And on the other side, because we have limited data, like 10 samples, discriminator can easily memorize these samples and then force generator to kind of generate exact samples. For example, here you can see real samples from a sketches domain, and a simple fine-tuning, a kind of classic fine-tuning done by TGAN paper uh, results in repeating the training samples. As you can see, lots of generated samples are exactly similar to the training samples. The third task is unconditional generative modeling under data constraint with pre-trained generator and cross-domain adaptation using text prompt or UGM3. So this task is similar to UGM2, but the difference is that we don't have any samples from target domain, and we just have a text prompt that describes the target domain. This is a zero-shot classification task. And as an example, NADA gives a solution for this. It defines a directional loss in clip space to adapt, for example, a pre-trained GAN on FFHQ using 3D render in the style of Pixar as input. And you can see the results. So the generated images are indeed in style of Pixar. Or it can adapt a pre-trained GAN on AFHQ dog using Joker as input. Now we have this image of the dog but we add this style of joker on top of it. The major challenge of this task is adaptation to distant domains, as the similarity between source and target domain decreases. Without having any sample from target domain, that would be really hard to adapt. For example, you can see some results from adapting dog to capybara. Because of the difference between source and target domains, the quality of the adapted samples are degraded a lot. Task number 4 is conditional generative modeling under data constraints. We call this CGM1. And here we are given case samples with class labels from a domain. And we want to learn to generate diverse and high quality samples conditioned on the class labels of the same domain. So here we basically want to train a conditional generative model from scratch, but we have limited data from that domain. A solution, as an example of solution for this, we have CBC approach, which proposes a switch from unconditional training to a conditional one during training. So they have a very simple but cool mechanism to do this. They start with unconditional training, which is more stable under limited data, and switch to conditional one. We will discuss more details later. And as you can see, it can conditionally be trained on 20 classes of ImageNet carnivores using only 100 samples per class. And here we can see the comparison between CBC and StyleGAN to ADA. For example, for generated bear samples, CBS has a very good quality and also the diversity, different poses and different angles. Task number 5 is conditional generative modeling under data constraint with pre-trained generator. In this task, we are given a pre-trained generator on the scene classes of a domain. So the domain is divided into scene classes and unseen classes. We have a generator which is trained on the scene classes. And in addition to that, we have case samples from unseen classes. Here we want to use the knowledge of the conditional generator trained on scene classes to be able to generate samples from unseen classes. As an example, Lofcan uses meta-learning to learn from 85 classes of flowers to generate images. So for each of these classes, we are given a few samples, and Lofcan learns to how to generate new samples using these few samples. And then it applies this knowledge for few-shot image generation on unseen classes. Task number 6 is conditional generative modeling under data constraint with pre-trained generator and cross-domain adaptation. So this cross-domain adaptation is important because the previous task CGM2, the seen and unseen classes, both of them were from the same domain. But here we have different domains. Here we are given a pre-trained generator on a source domain. In addition to this pre-trained generator, we have case samples with class labels from target domain. And we want to use the knowledge in pre-trained generator to be able to generate diverse and high quality samples from target domain. But this is a conditional generation. So this generation is conditioned on the labels. As a solution, for example, here we have visual prompt tuning, which adapts a pre-trained conditional generator on ImageNet to another dataset, places 365, with only 500 images per class. Task number 7 is quite a different one. Here we have internal patch distribution generative modeling, or IGM. And usually we are given case samples from the same scene. And we assume there is a rich internal patch distribution within these samples. And here we want to learn the distribution of the patches, not the distribution of image itself. And after learning the distribution of patches, we want to generate new samples which has the same patch distribution but with different layout. One cool thing about this figure is that after preparing this figure for our survey and publishing new draft, I saw a news about a decision on adding a force tower to Marina Bay Sands, which was quite cool. As an exemplar solution, we have this SynDDM paper, which uses a conditioning mechanism on diffusion models to be able to perform this IGM. And one example is to use a single image of pyramids, learn the internal patch distribution, and then learn to generate variants of it. For example, here they have added some parameters to the original one. And finally, task number 8 is subject-driven generative modeling, or SGM. This task was introduced newly when we were writing the first draft of this survey, but as of now, this is a very popular task and it has attracted a lot of attention, and lots of papers are published addressing this task. Here, we are given a pre-trained generator, which is very capable of generating diverse images. In addition to that, we have case samples of a particular subject. As an example, we have case samples of a particular backpack here. And then we have a text prompt that describes our desired image output. And the objective is to learn to generate diverse and high quality samples containing the same subject. As an example, Dreamboost paper fine-tunes a generator using only 4 images of a particular dog. And during fine-tuning, they link these images to a unique token. Here we denote it with V. And after that, they are capable to generate different variants of this subject by including a new text. For example, we can have a V dog in Mountain Fuji. So the same dog is being generated in Mountain Fuji, or we can have a dog with Eiffel Tower in the background. This task also enables other cool applications and other tasks. For example, we can have color modification. The car on the left side, we can learn it as a V car. And after learning this, we can generate different colors of this car. For example, a purple V car, a red V car, or a yellow V car. Another interesting application is generating these hybrids, which is quite cool. For example, given this input image, we can learn this V dog, and then we can generate hybrids. For example, a cross of a V dog and a bear, a cross of a V dog and a panda, koala, lion, or hippo. And these generated images are really cool. Next thing we are going to discuss is the major challenges of generative modeling under data constraints. And as you can see, our elephant is a bit sweaty because of these challenges. If you are interested, I have generated this image using Qwen image because it has very powerful performance in terms of generating text within an image. If you are interested on a technical video on Qwen image, just let me know on the comments. Main challenges are 3 parts: challenges of training, sample selection, and evaluation. First, we discuss the challenges for training, which includes overfitting, frequency bias, modeling distant domains, and identifying and removing incompatible knowledge. We start with overfitting. Overfitting is a common issue in machine learning when powerful models start to memorize the training data instead of learning some features which are generalizable to unseen samples. As an example, consider this cool diagram from Geek for Geeks. Here we have 2 classes. The green crosses are representing one class and yellow circles are representing the other one. There are 2 samples from green classes which are inside the yellow classes. It could be because of issues on the learned features, or it could be because of some noise in the data collected. The ideal case is learning this boundary as curve, which kind of separates these 2 classes with a good accuracy. If our model underfits, as you can see on the left side, the learned boundary is too simple to explain the variance. We have lots of error. And if our model overfits, it tries to include these outliers, 2 green crosses, within the boundary. And the learned boundary is very complex and overfitted to training data. So if it is used for unseen data, it won't perform very well. In terms of training and validation loss, we can also observe overfitting. If overfitting happens, the loss on training data is reduced. This could be for discriminative task or generative task. But the loss on validation data, which was unseen during training, is still high. So this difference in the loss shows that our model is overfitted to the training data. We have similar observations for training generative models. For example, this is a plot from ADA paper. They show that when we are training a GAN, the FID is started to decrease. After a while, it saturates, and after that, it starts to increase. And as we decrease the number of training samples, this happens sooner. So the final FID increases. And they have this cool plot also for showing the confidence of the discriminator about real samples, which is an indication of overfitting. On the left side, you see the plot for the case when we have 50,000 training samples. On the right side, you see the plot when we have less number of training samples. As you can see, when we reduce the number of samples in training a GAN, the discriminator becomes more confident and the divergence between the scores of real and fake images is more severe. And under extreme cases, when we have few shot data, say around 10 shot of data, the generator just learns to replicate the training data. Second training challenge is frequency bias. This ICML 2019 paper from Yashua Bengio's group shows that neural networks learn lower frequencies first. To explore that, they have designed a regression experiment. They have this regression task and they want to train a model to fit these sinusoidals, and each sinusoidal is related to a particular frequency. And the plot on the left side shows that in the beginning of training, the model has learned the lower frequencies, but the magnitude of the generated higher frequencies is around zero. As training goes on, the model starts to learn more and more higher frequencies. We have a similar observation for generative models. This AI 2022 paper shows that generative models prioritize fitting low frequency components and usually disregard the high frequency components. And for this, they have this cool analysis. They train StyleGAN2 on fractal-based datasets. On the left side, you can see the sample itself, and you can see the frequency components of the sample. The leftmost plot shows the Fourier transform coefficients. The center is related to lower frequencies, and as we move away, it shows the higher frequencies. And they have three different boxes. Black box is related to lower frequencies. Green box is related to mid frequencies and yellow box is related to high frequencies. They plot the same thing for generated image with StyleGAN2. And as you can see, if you compare the two black boxes, you can see that StyleGAN2 is capable of generating lower frequencies. But for middle frequencies, the generation capability is not that good. And for higher frequencies, StyleGAN2 almost disregards the generation of these frequencies. This property of the generated images is usually used by several works for deepfake detection. For example, this CVPR 2021 paper from our group shows an analysis about this. Because the higher frequency of the real and fake images are different, we usually can train a classifier on spectral domain and detect generated images based on their frequency. So we learned about this bias and about this issue for image generators. And this bias worsens when data for training is limited. For example, we have this training data of grumpy cat and art painting. We have 100 images from each of these domains. If we train a fast GAN on these data sets, the generated images show loss of high frequency detail. You can see some loss in ears of generated cats, or you can see that the higher frequencies of the generated art paintings are quite mixed together. Exclusion of these high frequency components, as you can see, results in missing the details of the image. The third challenge is modeling distant target domains, and this is specific for transfer learning scenarios. And why we discuss this and why this is important, it's because a large amount of works in generative modeling under data constraints are based on transfer learning idea. And as we discussed before in tasks, transfer learning tries to leverage the information from a source domain. So we have a generator trained on a source domain. And for this source domain, we have a lot of data. So the generator is very capable, very powerful. And we want to transfer this knowledge for a target domain. For example, here source domain is human faces and target domain is sketches of human faces. In our recent NeurIPS 2022 paper, we analyzed the setup for related works in the literature and show that a large amount of research in transfer learning is focused on target domains that are semantically similar to the source domain. For example, transferring knowledge from a pre-trained generator on human faces to babies. And we plot these setups over here. FFHQ, which you can see in dark blue, is source domain, and lots of works focus on babies and met faces. And we plot the samples for all these domains on this image. And as you can see, the distribution of the babies and met faces is very close to the FFHQ. On the other hand, we have other domains like cat, dog, flowers, or church. And as you can see, their distribution is quite distant from FFHQ. And the majority of the works in the literature do not consider these target domains. Here's an example for 10-shot image generation, where the source domain is human faces and the target domain is babies. Most of the approaches are capable of generating good images here. But when we consider transferring knowledge from human faces to cat faces, majority of the related works fail. And the final training challenge is identifying and removing incompatible knowledge. And this is also specific for transfer learning. We showed this for the first time in our CVPR 2023 paper. And the concept is that some encoded knowledge in source domain are incompatible with target domain. And if we kind of transfer this knowledge, it will be harmful for image generation for target domain. As an example, consider that source domain is church and target domain is sailboat. Usually we have some greenery in church, which is incompatible knowledge to sailboat domain because boats are in the middle of sea and we usually don't have greenery in the middle of sea. The next challenge is the challenge for sample selection. Based on our review, even though there are lots of works in the literature that discuss generative modeling under data constraint, sample selection or data-centric approach remains challenging and relatively unexplored. As an example, we have designed an experiment for 10-shot image generation. And here we adapt a source generated trained on FFHQ to target domain AFHQ cat using only 10 samples. And for this adaptation, we use a state-of-the-art model. We performed this adaptation for 3 times. The setup is exactly the same for each of these experiments, but for samples, we just randomly 10 samples from AFHQ cat as our training samples. As you can see, the final FID for these experiments could vary a lot. In the best case, we have an FID around 40 something, but for worst case, the FID is 90, which is really a large gap in terms of image quality. And this shows that generative capabilities under data constraints are significantly influenced by sample selection. If I have like 70,000 samples, the influence of each training sample is not that much. But if my samples are reduced, the number of samples are reduced to like 10, 50, each sample has a very significant impact on the training process. And final challenge is the evaluation challenge. We have some existing challenges for evaluating generative models when we have enough data. But under low data regimes, this becomes even worse. In the literature, the main attributes for evaluation of the generation capabilities are quality and diversity. The most common metrics for evaluating generative models under data constraints are shown in this table, including FID using clip features, KD, inception score in trial PIPS, single image FID, image text similarity, and user feedback. But there are some challenges with current metrics. First one is that statistical measures like FID, KID, and inception score lose their significance when dealing with limited data. And what we mean by that, for example, FID is introduced in this NeurIPS 2017 paper. And how this is calculated, we have real images, we pass it through inception network as feature extractor. We do the same for generated images and extract the features for both real and fake images. Then we calculate the mean and variance of the distribution of the features for both real and fake. And based on this similarity, we decide whether generated images are following the same distribution as real images or not. Under data constraints, say we have only 10 samples, the mean and trace components that we are calculated for FID are not that accurate, and that's the issue. Second issue is that we don't have a unified framework for subjective evaluation or human judgment. Each paper has its own way of doing this, which makes the comparison between papers a bit hard. And finally, usually the metrics that we use rely on deep features extracted from pre-trained networks. For example, as we discussed before, FID is using inception features, and the inception model is trained on ImageNet 1K. This could be good as a general purpose feature extractor, but might not be optimal for out-of-domain data. Next, we start our comprehensive review of proposed approaches for generative modeling under data constraints. We categorize the proposed approaches in the literature to 7 different categories. And we start with first one, which is transfer learning. Transfer learning itself has 6 subcategories. And we will start with a brief discussion about transfer learning itself and then discuss subcategories. Transfer learning in generative modeling aims to transfer the knowledge of a pre-trained generator, which is trained on a large and diverse dataset, to a target domain with limited data. How we do this, assuming that source generator is denoted by GS, we initialize the weights of our generator with weights of GS, then fine-tune our generator using limited data from target domain. And the idea is that there are some general knowledge or domain agnostic knowledge from source generator which are useful for our target domain. We want to preserve this knowledge. And then there are some domain specific knowledge from target domain, and we need to acquire this knowledge. And we acquire this knowledge by fine tuning on the limited data from target domain. As an example, if we want to train a generator for a target domain like Van Gogh's house, because there are not that much paintings from this target domain, we have limited data. And what we can do, we can use a pre-trained generator which has some shared knowledge. As an example, here we can use a pre-trained generator which is trained on Elson Church dataset. The structure of the church, the greenery can be shared knowledge, and the domain specific knowledge is the style of the painting. But there is a major limitation because we have data constraints on target domain. The general knowledge can be degraded during fine tuning because of overfitting. As an example, if we want to adapt a source generator trained on images of human faces, for example, FFHQ dataset, to painting of human faces. In this scenario, what is shared knowledge? Shared knowledge could be like face structure, diversity in pose, hair style, and other things. And the domain specific knowledge is the style of the painting with the particular artist we want to adapt to. If we use conventional transfer learning, just fine tune the model without any mechanism to preserve the source knowledge, what we happens is that we lose the diversity and we only adapt the style of the target domain. Here's an example from EWC paper. As you can see, we have 3 training samples, and after adaptation, all generated images are basically similar to the training samples, meaning that the diversity of the source generator is lost. And approaches in this category actually want to prevent that. And the first subcategory is regularizer based fine tuning. The approaches in this category add a regularizer term to the main training objective to preserve the knowledge in the pre-trained generator. One of the first works in this category is elastic weight consolidation, or EWC, inspired by popular EWC work for continual learning. This is presented in NeurIPS 2020. And their goal is to preserve the diversity of the source generator while adapting the style of the target domain. This is one of the first papers that discusses few-shot image generation. They have a key observation, and they mention that in neural networks, usually weights have different level of importance for a target task. This target task could be image classification, could be regression, or could be image generation. Usually, a subset of weights in neural network are important. If you degrade them, the performance will degrade severely. And there are remaining weights. There are some weights which are not that important. If you discard these weights, the performance of the network won't be affected that much. And this is also the basis of approaches like weight pruning or network compression. They usually prune or compress the weights which are not that important. And EWC wants to use these concepts for future image generation. And their objective, based on this concept, is that we have some important weights for image generation, and these important weights are encoding the rich knowledge in source domain. What we want to do, we want to detect these weights and make less change to these weights during fine tuning so we can preserve the knowledge. And the remaining weights, which are not that important, we can update them to obtain the domain specific knowledge. For measuring importance, they use Fisher information, which measures the change in loss by perturbing a particular weight. And it can be estimated by gradient of the loss with respect to parameters, the second order gradient. Here, f denotes the Fisher information. And for each single parameter within neural network, we have a scalar value in f showing its importance. If the value of f is high, it shows that this weight is very important. And if the value of f is low, it shows that the weight is not that important. So they use this property and add a regularizer to penalize change in important weights. As you can see in the term added here, if theta I is an important weight, fi would be also high. And we don't want to change that, because if we change that weight, the penalty would be high. But if theta I is not that important weight, we have permission to kind of update that weight. And these are some 10-shot adaptation results from EWC in 2020. They adapt a generator pre-trained on FFHQ to emoji dataset. And as you can see, compared to previous works, it has better quality and better diversity. Approaches like NST, they don't have good quality. BSA kind of fails to generate all components of human face. And MindGAN, even though the generated samples have good quality, they are replicating the few-shot training samples. And this table shows a quantitative comparison between different approaches. FID, the less is better. As you can see, EWC has the lowest FID. LPI-PACE is used to measure diversity. And based on user feedback, 48% of the users prefer generated images by EWC. And this is a cool table showing the effect of the size of the target dataset, starting from one shot, going to 10 shot, 100 shot, and 1,000 samples and 10,000 samples. By increasing the number of available samples from target domain, the performance of the approach is being improved. Next work is cross-domain correspondence, or CDC. And the key observation of CDC is that within generated images of a good and powerful source generator, there is a correspondence. And if we fine tune this source generator to a target domain with limited data and overfitting happens, this correspondence will be degraded or vanished. As an example, in this image, the first row shows generated images for four latent codes, Z0, Z1, Z2, and Z3. And as you can see, there is a correspondence between these samples. By correspondence, apparently they mean similarities and differences, both similarities and differences. If fine-tuning overfits, these similarities and differences are vanished. As an example, in the second row, the generated images by latent code Z0 and Z1 uh, are kind of similar. The similarities and the differences that we had before, all of them are vanished, and we just have two similar images. And CDC wants to preserve that. And as you can see in the third row, the differences between two images are kind of preserved, but the style of the target domain is adapted. And how they do this, they add a regularizer to preserve the correspondence between generated images before and after adaptation. And for this, they have two generators. They freeze source generator, and then they have an adapting generator which starts from source generator and is being fine-tuned uh, on the data from target domain. They sample n+1 noise vectors, and for each of these noise vectors, they generate images with both source model and adapting model. So for example, we have n+1 images generated with source model, the ones you can see on the left side, and we have n+1 images generated by adapting generator, the ones you see on the right-hand side. Then they compute pairwise similarity scores between images generated by these generators. For the left generator, they compute the similarity between images generated by Z0 and Z1, Z0 and Z2, Z0 and Z3, and so on. They call this S1S, S2S, and S3S, and so on. So this is a similarity score. They compute this in a feature space. They do similar thing for the adapting generator. For generated images by Z0 and Z1, they get S1T. Generated images by Z0 and Z2, they get S2T, and so on. After this, they have n similarity scores for source generator, and they have n other similarity scores for adapting generator. They pass these scores to a softmax operator, and they get two probability distributions, one for source generator and second for target generator. Here, the first row of the formulation is for the source generator, and the second one is for target generator. And then they enforce these two distributions to be similar by a KL divergence term. And these are some samples of 10-shot adaptations from FFHQ to sketches. If you consider the generated images by source generator as an anchor, compared to other works, CDC is capable of preserving the diversity. For example, the hat, the pose, and all these differences in the source generator are preserved in generated samples with CDC. And these are some quantitative results in terms of FID. As you can see, for 10-shot adaptation from FFHQ to babies, sunglasses, and sketches, CDC is giving the best results. And table 2 is for computing the diversity. They propose a new metric. They call it intra-LPIPS. And how they do this, we have 10 training samples. In a feature space, they kind of find the embeddings for these 10 samples. Then for generated images, say around 5,000 generated images, they map these images into embedding space, and they cluster it around the training samples. And then within each cluster, they compute diversity, and then they average diversity over all clusters. This gives a single scalar value, which shows the diversity of the generated images. The higher diversity means that images are have more variations. And as you can see, CDC here gives the best results for all three target domains. The second subcategory of transfer learning approaches are latent space approaches. And these approaches usually explore the latent space of the source generator to identify suitable knowledge. So instead of focusing on the parameters of the generator, they kind of mine the latent space. First work is the CVPR 2020 work. The name is MineGAN. And the idea is that they perform this knowledge selection by mining the latent space of the pre-trained generator. For this purpose, they use a miner network to transform the latent space, Z, in a form that generated images are more similar to target domain. And this has two main advantages. First one is that miner network has less parameters. They use an MLP for this. And because of having less parameters, this prevents overfitting. And second thing is that mining step disposes the pre-trained GAN to sample from a narrower region, which is good for target distribution. And they have a two-step training for this. In first step, they have this miner network denoted by M. They train it from scratch. G is frozen and D is being fine-tuned with a smaller learning rate. Once M is trained, in second step, they fine-tune all networks. There is another paper, recent paper, ICLEAR 2023. The name is Latent Code Learner. It uses a very similar idea to MindGAN, but with two main changes. First change is that they make the mapper network more compatible to StyleGAN2. Now they map Z into the extended latent space of StyleGAN2. And second thing is that they add a style loss using VGG 19 features to improve image generation quality. Third subcategory of transfer learning are modulation approaches. Modulation approaches usually freeze the weights of the source generator and add learnable modulation weights on top of it. The first work that discovers this is GAN memory in NUDIPS 2020. And in GAN memory, they modulate the weights of the source generator to adapt it to target domain. And they have a very cool setup. The setup is lifelong generative learning. I think it is one of the first works that kind of explores this setup. Lifelong learning is the extended version of continual learning. In continual learning, tasks are coming continuously. As an example, you learn a network for your first task. It could be a classification, say, between cat and dog. Once you learn this, the second task comes after a while. When you are learning second task, you are using the data from second task and you don't have access to data from first task. And the goal is to learn second task without forgetting first task. If the tasks never stop, we call this lifelong generative learning. And GAN memory uh, tries to address lifelong generative learning, meaning that the tasks now are image generation tasks. And what they do for this, considering base task as D0, they have some weights for this base task. This is a generator pre-trained on a source domain. They freeze the weights of this base task. And then for each upcoming task, they learn separate modulation weights. For example, we have task D1. We have some modulation weights for this task. We are learning this from scratch using limited data. It is called G1 and D1. Then task D2 comes. The parameters of the source generator are still frozen, and we learn separate modulation weights for this domain. It is separate from the modulation weights learned for task 1. And then for other upcoming tasks, we do the same thing. This is the modulation they use. They have a slightly different version of it for fully connected layers and convolutional layers. The weights are first normalized, and then we have a scale and shift transformation as modulation. And this is the experimental setup for GAN memory. For D0, they consider human faces, meaning that the pre-trained generator is trained on human faces. Then there is a generation task coming from flowers, church, cat, brain tumor, chest x-ray, and any. And how this works, so the first column is D0. This is generated images from human faces by pre-trained generator. Then second column is where they freeze the parameters of base generator and learn modulation weights for flowers. As you can see, because the weights for source domain was frozen, the generator still can generate images from source domain. And if we add the modulation weights of flowers domain on top of this, we will be able to generate images of flowers. Then another task comes, which is a church dataset. We learn separate modulation parameters for church dataset. Now we have frozen weights, we have modulation weights for flowers, and we have separate modulation weights for church. And because of that, we are capable to generate images from all these three domains. Another work is adaptation-aware kernel modulation, or ADAM. This is our work in NeurIPS 2022. And this work uses modulation for few-shot image generation. And the idea is to preserve the knowledge of the important kernels. After finding important kernels, the knowledge on these kernels are being preserved using modulation weights. And here we apply kernel modulation technique, which is a low rank modulation to prevent overfitting. Next subcategory is natural language guided, and approaches within this subcategory use the feedback of the vision language model to adapt the source generator using text prompt. As an example, we have this work, StyleGAN Nada, which adapts a generator to a target domain using only text prompt. And they do it by kind of leveraging the clip embedding space. This is the setup we have. In this setup, G-frozen is known. We know we have a pre-trained generator. And then we also know the text prompts for source and target domains. For example, here we have photo for source domain and we have an in painting for target domain. So the trained generator is what we want to obtain. And how they do it, they propose a directional clip loss to train this model. As an example, if we consider source domain dog and target domain as cat, the main idea is that in clip embedding a space, the embedding of image of the dog is close to the embedding of text of the dog. And same for cat. They use generated images by source generator as images of the dog, and they use fine-tuning generator as the expected image of the cat that should be kind of generated. And based on that, they calculate an offset for text. They call it delta t. They calculate an offset based on image. They call it delta I. And then they define this directional loss to align these two offsets. And based on that, they are able to fine tune the generator. And these are some results of adapting a source generator pre-trained on FFHQ to UQO-E painting using just a text prompt. And these are some other results on adapting a pre-trained generator on AFHQ dogs to the Joker, which are quite cool. An extension of NADA approach is this image-specific prompt learning, or IPL, presented in CVPR 2023. And the idea of IPL is that for a specific source and target domain, NADA always uses a similar direction for all samples, and it fails to consider the details within samples. For example, in this figure on the left side, you can see that NADA uses same direction for all three samples when it is adapting a generator from human faces to the Tolkien elf. But they mentioned that if we consider the nuances, for example, first sample could be Asian girl human to Asian girl Tolkien elf. The direction could be different for this because now we have this additional information, Asian girl. Second sample is curly hair lady human. And if we add these additional information, we might have a different direction. And they try to address this by introducing a specific direction for each pair. And how do they do this? they basically learn these tokens for each image. So here, using latent code, we pass this latent code to generate images with each of these latent codes. Then the same latent codes are passed through a latent mapper. And latent mapper is supposed to generate image specific prompts. These image specific prompts are being added to the prompt we already have from source or target domain. And then what they do, they use clip embedding space to learn these prompts for each of the W latent codes. So they basically pass the image and corresponding prompt to the vision and text encoder of clip, and they use a similar loss used in clip paper to learn these image specific prompts. And these are some results from IPL. For example, when we are adapting from photo to Disney, they mentioned that because NADA always uses a fixed direction, we have some artifacts. For example, all generated samples have the same kind of nose, and this can be mitigated in IPL. Another cool work, which is addressing a new task, is textual inversion in iClear 2023. And their idea is to invert an image of a subject to a textual description. For example, on the left-hand side, you have three images of a specific toy cat. They take these samples and they try to invert this to the embedding space of a text to image generation model. So they get S star, which is a text embedding in this embedding space. And then once they learn this S star, they can kind of attach this S star to any text prompt and generate new images. For example, we can have painting of two S star fishing on a boat or a S star backpack. As we discussed before, this is subject-driven generative modeling task. And how they perform this inversion, it's quite a simple approach. So they freeze all parameters within text-to-image model. For example, here they use latent diffusion model. And then they pass these images to a latent diffusion model. On the text side, they pass this photo of S star. The tokens for a, photo, and of, all of them are known. Here, for example, you can see them as 73500, 701. But the tokens for S star, they are not known. And they condition image generation on this text prompt, and they get a loss. And then they backpropagate the loss to learn these unknown tokens. The next subcategory is adaptation-aware approaches, and these approaches mention that to preserve the knowledge of source domain, we should also consider the target domain. And the idea is that, for example, if I want to adapt a source generator pre-trained on FFHQ to target domain 1, as an example, anime painting, some weights and some source knowledge are important. And then when I want to adapt the same generator to another target domain like sketches, another subset of source knowledge could be important. So I need to consider this adaptation itself instead of just considering source domain. So Adam is the first work that discusses this. And in Adam, we use importance of the kernels for adaptation from source to target domain. We modulate all weights using KML, and we perform adaptation for a small number of iterations. And during this adaptation, we use Fisher information on modulated weights to kind of detect the important weights. After this, we obtain Fisher information for all kernels within a source generator, and then kernels are classified into two classes: low importance kernels and high importance kernels. High importance kernels are being preserved using a modulation, as we discussed before, and low importance kernels are being fine tuned to obtain the domain specific knowledge. Another work is remove incompatible knowledge, or RIC. This is also from our group, a CVPR 2023 work. And here we measure the importance of the kernels for adaptation from source to target domain in a dynamic manner. And what happens is that during adaptation, in particular iterations, We compute feature information for all kernels and classify them to three groups. The filters that needs to be preserved, these are the important filters. The filters that can be fine-tuned, these are kind of uh, in the middle. And then we have less important filters, filters to be pruned. And this is also connected to the concept we discussed before in compatible knowledge. We mentioned that the filters which have lowest feature information are kind of connected to the incompatible knowledge. So we prune them to prevent transferring this harmful knowledge. And finally, the sixth subcategory is prompt learning. This is a quite new idea. And in this idea, the approaches freeze the source generator and add or generate visual prompts to guide generation. Visual prompt tuning or VPT presented in CVPR 2023 is the first work that discusses this idea. And they learn visual prompts for steering the image generation of a pre-trained generative vision transformer. And they discuss that generative vision transformers include three steps. We have image quantization, which usually uses a VQ-VAE to convert image patches into indices. And then we generate image tokens based on these indices using a autoregressive or non-autoregressive transformer. At the bottom, you can see that autoregressive kind of has this left-right manner, and non-autoregressive is just randomly generating the tokens. They add this visual tokens, learnable visual tokens with green color before the generated tokens to steer this image generation. And the results show that they are capable to generate images better than kind of uh, strong models like Big GAN. Next category of works are data augmentation approaches, and we have three subcategories here. Data augmentation aims to increase the quantity and diversity of the training data. And they do this usually by applying some transformations on real data, like adding noise, rotating image, and other transformations. And this results in increasing the data quantity, which can prevent overfitting. For example, we can have pixel bleeding, general geometric transformation, or color transformation to increase the quantity of our data. But there is a major limitation using classical data augmentation in generative learning. Generator thinks that this augmented data distribution is the real data distribution. It learns this transformation and then generate images which are rotated or have, for example, pixel bleeding, which is not useful for us. And data augmentation approaches in generative learning propose to prevent this. First subcategory is image level augmentation, where the transformation is applied on image space. First subcategory is image level augmentation, where the transformation is applied on image space. As an example, we have adaptive data augmentation or ADA in NeurIPS 2020, and they apply augmentation on both real and fake images with an adjustable probability based on the training dynamics. Their approach includes following components. So on the left side, we can see the learning path for a generator of the GAN, and on the right side, we can see the learning path for the discriminator. They apply augmentation on both real and fake images. The augmentation is applied with a probability less than 1, and this helps the occurrence of the real distribution and prevents leaking these augmentations to generator. And the strength of the augmentation is adjusted based on the degree of overfitting. To do this, they propose two heuristics to monitor the overfitting, RV and RT. R equals to 0 means no overfitting, and R equals 1 indicates complete overfitting. When R is higher, it shows that overfitting is increasing. In that case, they increase P to have more augmentation and decrease overfitting. These are some samples generated by ADA for breast cancer data. On the left side, you can see real images. In the middle, we see the images generated by ADA. And on the right side, you can see images generated by StyleGAN2. So there is a meaningful difference between FID of ADA, which is around 15, and FID of StyleGAN2, which is around 97. The gap is really high, which shows the efficacy of this ADA for limited data scenarios. And this is another example for MetFaces dataset, which are art paintings of human faces. Another approach is patch diffusion, which is proposed for diffusion models. This approach crops random size patches from the input image and then performs score matching on the patch level. So here, for example, we can see we have different patches of input image, and then the coordinate of the patch, I and J, and scale of the patch, S, are also added to the learning objective. Next subcategory is feature level augmentation, and these approaches apply data augmentation on feature space. As an example, we have this adversarial augmentation paper from NeurIPS 2021, and they add adversarial noise to the features of the real and fake images in both G and D. And by adding this noise, they want to increase the robustness of both G and D. For example, as you can see here, when we are updating D, the added noise to these samples are optimized to flip the label. For example, the objective of noise added to D1 of X is to change the label from real to fake, and same for delta hat, which is added to the features of fake image to switch the label from fake to real. And they have a similar mechanism for the features of G. And the final subcategory is transformation-driven design, which leverages the information of individual transformation. As an example, we have this data augmentation optimized for GAN, DAG, from our own group in TIP 2021. And in this work, we use a separate discriminator for each transformation. So for real and fake images without any transformation, we use a discriminator denoted as D. For transformation T2, we use discriminator D2, and similar for other transformations. The idea is that by exposing a particular transformation into a separate discriminator only focuses on the features which are related to real and fake images and discards the features related to transformation. And in this way, the transformations won't leak to our generator. Next category is network architecture, which itself has three subcategories. In this category, the approaches usually design specific architectures for the generators to improve their training performance under data constraints, like designing shallow or sparse architectures to prevent overparameterization and then prevent overfitting. There are some challenges in this category. First thing is that when you design a new architecture, you will always have some problems with discovering the optimal hyperparameters. And the second one is that if we design a new architecture, it would be hard to leverage the powerful pre-trained generators we have in the literature. First subcategory is feature enhancement. The approaches in this subcategory design additional modules to enhance or retain the features of the generator. As an example, we have FastGAN from iClear 2020, which has three major design choices. They use a compact network for both G and D to prevent overfitting. They introduce skip layer excitation for G for better gradient flow, and they add a self-supervised task for D to have additional signal for improving the learning of discriminator. And one cool thing about this approach is that back in 2020, it enables training a generator from scratch on high resolution images using only one RTX 2080 GPU and only 1000 images. On the left side, they have trained generator for 20 hours on nature photos. And for the images on the right side, they have trained generator for 10 hours on FFHQ dataset. This is the design for their generator. They use a single convolutional layer for each resolution, and they have this skip layer excitation, including skip connection between different resolution for better gradient flow. They also use a compact design for D, having less convolutional layers. And also in two different resolution, they add another task, a image reconstruction task like an autoencoder to have additional learning signal and improve the training of D. Next subcategory is ensemble large pre-trained vision models. And approaches in this subcategory improve architecture by ensembling pre-trained models. For example, we have this vision-aided GAN from CVPR 2022, and they add off-the-shelf vision models to enhance performance of the discriminator. And the idea is that because these powerful vision models have a very strong knowledge about the image itself, they can be used for real and fake classification. And how this vision aided GAN is using these vision models is that they discard the classification head of these vision models and they add another trainable head for real and fake classification. Next subcategory is dynamic network architecture. And in this subcategory, the architecture of the network is evolving during training. For example, we have this collapse by conditioning paper from iClear 2022, and they mentioned that under limited data, unconditional learning has a stable training, but we have issues with conditional learning. And because of that, they start with an unconditional learning and gradually switch to a conditional learning. They do this by a simple but clever trick. So on the generator side, they add this lambda. Lambda is used to add this class embedding. It starts from 0, and then as training proceeds, it is increasing. So gradually, we are adding this conditioning on the class label to the generator side, and generator is gradually moving from unconditional to conditional one. And then on the discriminator, we have two passes for loss. The bottom one is real fake classification, and the upper pass is predicting the class label for real and fake images. But the loss of the upper pass is multiplied by lambda. So at the beginning, the lambda is 0 and no loss is backpropagating to update the network, and the training is unconditional. And as we move forward, the weight of conditional training is being increased. Next category is multitask objectives, which has 6 subcategories. And in this category, the approaches introduce additional tasks during generative learning. And the idea is that solving this task provides additional feedback during learning process. And this additional feedback helps to learn generalizable features, which in turn reduces overfitting under data constraints. But primary challenge is that when you are designing a new task, from what we know from multitask learning literature, there is a potential of having a negative knowledge transfer. First, we discuss regularizer. In this subcategory, the approaches add a task objective as regularizer to prevent an undesirable behavior during training. For example, the GAN from NeurIPS 2022 observes that gap between the gradient of D with respect to real and fake images are increasing when we reduce the data, and then they add a regularizer to basically prevent this. Then we have contrastive learning, which introduces a pretext task to enhance the learning process. For example, we have DCL work in CVPR 2022 from our group, which uses contrastive learning for both G and D during fine training a pre-trained generator to a target domain. And contrastive learning is defined for both G and D. In contrastive learning, usually we pull positive samples together and push the negative samples away in feature space. And here's the detail. For G, the generated samples for the same latent code with source and adapting generator are used as positive pair, and then generated samples for different latent codes are used as negative pair. We have similar thing for discriminator. In the discriminator, the features of the generated images for the same latent code with source and target generator are used as positive pairs, and the features of the generated sample and real sample are used as negative pair. Then we have masking subcategory. In this subcategory, A part of the information is masked to increase the task hardness and prevent learning trivial solutions. For example, MaskScan is proposed in NeurIPS 2022, and it randomly masks out certain image information, including spatial and frequency, before passing them to the discriminator. So discriminator has less information. It increases the task hardness for discriminator, and in turn prevents learning trivial solutions for real and fake classification. They have two masking strategies. First one is shifted spatial masking. So they have a spatial mask, they randomly shift it, which results in masking certain patches of image, and the locations of the mask are kind of random. So the discriminator cannot memorize them. We have the same thing for frequency information. First, they extract spectral channels of the image, and then they randomly sample these spectral channels. So each time a discriminator is losing access to some random channels of spectral information. Another subcategory is knowledge distillation. And in knowledge distillation, we add a task objective to enforce generator to follow a strong teacher and distill this strong teacher's knowledge to the generator. For example, we have KDDL GAN from CVPR 2023, and they have two knowledge distillation or KD designs. The first one is distill the knowledge within image modality, and second one is to distill the knowledge of clip from both modalities. For the first one, they have two components. First component enforces D to mimic the vision encoder of the clip, which is a very powerful image encoder. And the second one prevents overfitting by decreasing the uncertainty. So they kind of push the features of the real images extracted by clip encoder to the features of the fake images extracted by discriminator. The second design is called correlated generative knowledge distillation. It has two components. First, they try to diversify text to image correlation, and then they distill the knowledge related to this diversification from clip vision encoder to the discriminator. Next subcategory is prototype learning. And this subcategory enforces learning prototypes for samples or concepts within the distribution. For example, we have this proto-GAN, which enforces prototype alignment. So they extract prototype for real and fake images, and they enforce these prototypes to be aligned. They also have some loss for the diversity of the images, so make this image generation diverse around the prototype. And finally, we have other multitask objectives. As an example, we have GenCo, which uses co-training for learning multiple classifiers that captures different perspective of data. Or we have AnyRes GAN, which uses continuous scale training, which samples patches with different sizes and learns a generator to output images with various sizes. And we also have diffusion GAN, which applies the gradual diffusion process on real and generated images during training GAN. At the beginning, we are using standard real and fake images, but as training proceeds, they use this diffusion concept and add some noise, which makes real and fake classification harder for D, increases task hardness, and in turn, trains a more powerful D. The fifth category of approaches is exploiting frequency components. And approaches within this category want to improve learning the generative model by reducing frequency bias. As we discussed before, generative models usually tend to learn lower frequencies and ignore higher frequency. And approaches within this category want to address this issue. As an example, we have FreeGAN from NeurIPS 2022, and it aims to reduce the frequency bias of the GANs by emphasizing on the learning of the high frequency components. And for this, they have three main modules. First, they add a high frequency discriminator, which performs real fake classification based on the frequency components. So in this image, On the right-hand side, after generated images, you can see the discriminator. And you can see the yellow box, which is extracting frequency information. So they use wavelet transformation to extract frequency information. And these informations are being fed to HFD, which is a light blue module, high frequency discriminator, which means in addition to features itself, discriminator is using the frequency information for real and fake classification. The second module is frequency alignment. As you can see on the frequency alignment is a gray box. And what they do, they extract the features of G and the corresponding features from D, and then they pass them to wavelet transformation to get the frequency information of these features, and then they try to align these features. And the final component is frequency skip connection. You can see it as a orange box on top of G. And this one is actually extracts the frequency information from each layer and feeds it to the another layer to make sure that this frequency information won't be lost. Next category is meta learning, which has three main subcategories. First, we discuss meta learning in discriminative learning. Meta learning is largely used to address few-shot learning problem, where, for example, we have five-way one-shot image classification. In this setup, we have five classes, and for each class, we are given one shot, one example of each class, and we are supposed to learn these classes using only one image per class. In conventional learning, we usually fine-tune our parameters on this data, but meta-learning tries to leverage some prior knowledge encoded as meta-representation and then use this meta-representation for better few-shot performance. One popular approach in the literature is episodic training, which matches the condition in which the model is trained and evaluated. This is proposed in Matching Nets in NeurIPS 2016. And the idea is that because in the test time, we will be given a five-way one-shot classification task, during training, we create tasks that kind of mimics this setup. For example, for creating task one, we randomly sample five classes from our training classes. And then for each class, we randomly sample one image. This creates our support set for this task. And then for the same classes, we sample some other images for evaluation, which creates our query set. The model will be trained on support set and then will be evaluated on the query set. The loss on the query set will be used to update our meta parameters. Same for task two, we randomly sample five other classes from training classes. For each class, we randomly sample one image as support set and other images as query set. So within each task, we have a rapid learning. And throughout this task, we have gradual learning, which learns the meta knowledge. This idea at the beginning was proposed for image classification, but it can replace with other tasks like regression, language generation, skill learning, or any machine learning problem. And in the literature, they use the same setup for image generation. So they try to learn meta knowledge from seen classes to improve few-shot generative learning on the unseen classes. Given a set of samples from seen classes, we create few-shot image generation tasks, and then we train the model on these few-shot generation tasks to get the meta knowledge. And then for the unseen classes, we will apply this meta knowledge for few-shot image generation. First subcategory is optimization, which learns the initialization weights from the scene classes as meta-knowledge to enable quick adaptation. As an example, we have this fast adaptive meta-learning or FAML approach. It uses an inner loop and outer loop approach similar to popular model agnostic meta-learning or MAML paper. The evaluation loss from inner loop is used to update the model weights in outer loop as meta-knowledge. Second subcategory is transformation. And in this subcategory, they learn sample transformation from the scene classes as meta-knowledge. For example, we have this age paper from CVPR 2022, and they explore latent representation of the pre-trained GAN to find both category agnostic transformation and category related transformation. As an example, you can see category related information on top, and you can see category agnostic information on the at the bottom. So for example, for category agnostic, the pose and rotation our category is agnostic. If you learn it from one category, you can apply it to another category. Their approach is to use mean value of the latent code for samples within a class as category relevant information, and then category irrelevant directions are learned by sparse dictionary learning and then being applied on top of these category relevant information to generate new images. The final subcategory is fusion. And in this subcategory, the approaches learn to fuse samples from the scene classes as meta-knowledge. Once they learn how to fuse samples, then they can apply this for unseen tasks. As an example, we have WaveGAN from ECCV 2022, which uses an encoder-decoder design. They first extract the features and then they learn how to fuse these features. And the final category is modeling internal patch distributions, which has two subcategories. In this category, approaches have major difference with conventional generative learning approaches. First one is that they learn the internal patch distribution of one image. They don't learn the distribution across many images. Second thing is that they generate samples with the same visual content or same patch distribution, but in a different layout. And approaches for this category need to learn a generative model from scratch using only one image, and in some cases up to three images. And finally, in this category, we need to learn a separate generative model for each image. And knowledge transfer is not explored in these approaches. First subcategory is progressive training. In this subcategory, we train a generative model progressively to learn the patch distribution at different scales or noise levels. As an example, we have seen the DDM paper from ICML 2023. It performs the diffusion and reverse diffusion or denoising mechanism in different scales. And after one scale, we have one upsampling and we perform it in an upper scale. And as we go forward, we increase the resolution. The second subcategory is non-progressive training. And in this subcategory, they train a generative model on the same scale or noise, but with changes to the model architecture. As an example, we have this one-shot GAN paper from CVPR 2021. This paper is inspired by style transfer literature and it separates the layout and content in real fake detection to overcome the memorization effect in one-shot setting. They also have a diversity term for generating visually different images. And finally, we discuss research landscape analysis and future directions. In this talk, we discussed eight different generative tasks under data constraints. A significant portion of the works, up to 80% of them, focuses on unconditional generation. Zero-shot unconditional generation is attracting more attention. And adaptation for in-domain classes has attracted a lot of attention in conditional generation. Conditional generation for out-of-domain classes using adaptation is not explored. And we have this recent task subject-driven generation. At the time of writing this paper, there were a few papers, but we were expecting that this would be a very kind of interesting future task. And as of now, more and more papers are kind of addressing this task. In addition to that, we propose another taxonomy for approaches. In this taxonomy, transfer learning is a predominant solution, which is capable of tackling a large number of tasks, more precisely 5 out of 8. And it can also handle all data constraint scenarios. The primary challenge in transfer learning is how to select and preserve the source knowledge which are good for adaptation. And majority of the works have studied GANs, but we can see more and more works are exploring training diffusion models under data constraints. An interesting thing is that the core idea of some of the approaches explored for GANs can be adapted for diffusion models. And here we discuss future directions. One interesting direction is harnessing the power of foundational models. We have very strong foundational models for image generation, like DALI, Imagen, Stable Diffusion, and others. And these models can be used in the context of generative modeling under data constraints. These models usually encode a vast amount of general concepts, but for specific target domains, they may not perform that well. And because of that, we can explore how to harness these models for specific domains. Second one is grounding zero-shot image generative capabilities. And by that, we mean that in current models, well-known concepts like Tolkien Elf is encoded properly and you can generate these concepts. But there are some new or evolving semantic concepts based on the time. So as of now, we may have some concepts or we may have some news or events which was not happened during the time of training these models, how we can include this evolving and new concept could be a very interesting future direction. Another interesting direction is knowledge transfer for distant or remote target domains. Based on our experiments in our survey and in our previous works, this has not explored properly, and usually current models fail under this setup. So this is also an interesting direction to consider. Data-centric approach is also another interesting direction. As we discussed in this experiment, because we have limited data, the impact of each data sample is much higher under data constraints, and data-centric approaches are not explored under these conditions. Finally, another direction is holistic evaluation of generative modeling under data constraints. We discussed difficulties in estimating real data distribution, lack of unified framework, and heavy reliance on some pre-trained feature extractors. And all these directions can be explored for having a better and much stronger evaluation approach for generative modeling under data constraints. Thank you for listening to this quite long talk. And if you have any questions, just drop some comments below, and I will be more than happy to answer your questions. See you on the next one.